Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem finding the median in a row-wise sorted matrix. Now what does the problem state? The problem state that you'll be given M cross N matrix, right? Like over here you can see a 3 cross 3 matrix is given, and the matrix will have all its row sorted. If you check out, all the rows of the matrix are sorted like 1 3 6, 2 6 9, and 3 6 9. So and this n cross m will also be odd. This whatever is the n cross m value, like 3 into 3 9, that's definitely going to be odd. Now out of all these integers, you need to tell us what is the median among all these integers. Like over here the median will be 6. Now how do you find out the median? It's super simple. If you write all these integers in the sorted order, you're gonna get something like 1 2 3 3, and then a 6 6 6, and then a 9 9. So if you figure out which is the middle element of the sorted, all these sorted elements, the middle element is 6. Now whichever is the middle element of among all the sorted elements, that is known as the median of the matrix. So this is the very simple question that you need to figure out, and there's one constraint which states that all the array elements can be between 1 to 10 to the power 9. That is what the constraint states. Again, this can vary because it can be minus, it can vary, right? But let's assume that we are solving this problem keeping the constraint as that the array integers or the matrix integers can be between 1 to 10 to the power 9. Now if this question is asked to you in an interview, which is the first approach that you will give to the interview? It's definitely the naive approach. What is the naive approach? You're going to tell the interviewer that you're going to iterate over every single element, like 1 3 6 2 6 9. Every single element you have to iterate, and while you're iterating, you put every element into some data structure, correct? Now once you have put it into some data structure, it can be a vector in C++, it can be a list in Python, it can be array list in Java, right? After you have put that, what you need to do is you need to sort that data structure in a linearly increasing fashion. Once you have sorted that, you will have the sorted array, right? And once you have the sorted array, you can definitely see that the middle index, yes, you can definitely see that the middle index is your median of your matrix, correct? So in this way, you can solve it using a very naive method. What will be the time complexity of this naive method? You're going to use an n cross m technique in order to put every element into the data structure. And in order to sort all these n cross m elements, can I say you'll be requiring a n cross m log n cross m time complexity to sort it. That's going to be the time complexity. But what about the space complexity? This data structure is going to store all the elements, so it's going to use an external space complexity of big O of n cross m. So obviously the interviewer will not be happy with the solution, and he'll ask you to optimize it. So the efficient solution will be using binary search. So let's understand that. So before moving on to the next part of the video, let me tell you about Coding Ninjas. Now, Coding Ninjas is one of the largest coding education company, and they have taught around 50k plus students. Now, they offer you courses in programming in different languages like C++, Java, Python. They also have courses for machine learning, Android development, data science, and web dev. The content quality is exceptional as it is made by experts from IIT, Stanford, Amazon, and Facebook. They do offer you 1:1 doubt resolving support, and the average doubt solving time that they take is literally the best in the market. Now, since the courses are really well structured and so many have benefited from it, I guess you should give it a try. And if you feel so, do use the link in the description to avail a discount, which will be added above the one which is already present in the website. So guys, go and check it out. Now, the efficient method will be using binary search. Now, how do you understand that it's going to use binary search? Because binary search is a method which is used to find an element in a sorted array. Now, if you have seen my previous video on finding the nth root of a number, you know that binary search can be implemented to any search space which is monotonic in nature. Now, search space is basically where your answer can lie. Can I say if I'm looking to find the median in these numbers, the median will be an integer somewhere between 1 to 10 to the power 9. Like over here, the median is 6. That's an integer between 1 to 10 to the power 9. So one thing I know for sure is the median is going to lie between 1 to 10 to the power 9. So I can say this is my search space. Now, how will I determine that this is monotonic in nature? So the thought process is something like this. If I figure out how many numbers are lesser than equal to 1 among all these numbers, I say that there is only one number. If I say how many numbers is lesser than equal to 2, I say there are two numbers. If I say how many are lesser than equal to 3, I actually say these are four numbers. If I say how many are lesser than equal to 4, I again say 4. If I say how many are lesser than equal to 6, I actually say 7 numbers. And if I keep on writing, I definitely see a monotonic increasing function. Yes, a monotonic increasing function. So if I can see such a pattern, I can definitely use binary search on it. Yes. And now how to use binary search? Let's understand in the next part. So the search space initially was from 1 to 10 to the power 9. So what I've done is I've shrinked the search space to 1 to 15 so that we can easily understand the algorithm. But when you write the code, please keep the search space as 1 to 10 to the power 9. Okay. So at first, let's try to find out the middle. Okay. So which is the middle? The middle is 1 plus 15 by 2. So the middle will be somewhere around 8, correct? Now, in order to implement binary search, just figure out how many are lesser than equal to 8. Yes, just figure out how many elements are lesser than equal to 8. So what you can say is, you will go on this matrix and you'll go at row wise, okay? And you try to figure out in this particular row, how many are lesser than equal to 8. So I can say in this particular row, there are three elements that is lesser than equal to 8, and this can be easily done using binary search. And I'll tell you that method once I've explained you this portion of binary search. Then I can explain you how to figure out how many are lesser than equal to 8 in a particular array, like how to find how many are less than equal to 8. I'll tell you that. So you figure out in the first row there are 3. In the next row I see that there are actually 2 numbers, so there are 2 more elements. In the third row I figure out that there are again 2 numbers. So what I can say is there are 7 numbers. Yes, there are 7 numbers that are lesser than equal to 8. So can I say including 8? Yes, can I say including 8, there are 7 numbers that are lesser than equal to 8, correct? And in order to find median, you know one thing, you're going to try to shrink this 7 numbers on the left, because median is something like this. A person, and there are 4 numbers on the left and there are 4 numbers on the right. Now one thing you know for sure is these 4 numbers might be equal, might be smaller, might be greater, but one thing is for sure, these 4 numbers are definitely lesser than equal to, and these 4 numbers are definitely greater than equal to, that is for sure. So don't you think you need to move this person to the left so that possibly you can get a better answer? Yes, because this guy is 8. Let's move this to the left so that this 7 might get reduced, so that you probably can place this person somewhere in the middle, right? So let's do that. So what I'll do is, instead of 15, I'll trim down my search space to 1 to 7, because I know 8 is having 7 elements that are lesser than equal to 8. So why don't I trim it down? Because something like 9, 10, 11, 12, 13, all these guys will increase only, but I want this 7 to go down. I just want it. I'm not sure if I can, but let's try it. So as of now, my search space has been reduced to 1 to 7. So why don't you try to figure out the middle? So the middle will be 1 plus 7 by 2, which is 4, correct? Now again, try to figure out how many are lesser than equal to 4. Yes, how many are lesser than equal to 4? And again, go to the first row and you figure out that there are a couple of numbers that are less than equal to 4. Again, go to the next row and you figure out that there is only one number. Again, go to the next row and you figure out that there is exactly one number. So there are 4 numbers. I repeat, there are 4 numbers that is smaller than equal to 4. Now, you know one thing for sure, your person is here, right? Your person is here and he is saying that including me, there are only 4 numbers that are smaller than me, right? Because me is 4 and there are exactly 4 numbers that are smaller than equal to 4. Now I definitely know this cannot be my median. This cannot be my median. Why? Because the median is someone who says I have lesser than equal to 4 on the left, and I say I have greater than equal to 4 on the right. Now this guy says including me I have lesser than equal to 4. That's not possible, because just imagine, even if you take something like 1 2 3 3 3, just imagine you take these guys and you say 3 is the median, you say 3 is the median. So even if you are wanting to find lesser than equal to 3, if this is the median, there will at least be 5 numbers, right? If there are 4 numbers, that means you're currently standing, the person is currently standing here. So apparently a person has to move right, correct? Just think on this, just think on this. Because 4 numbers including himself, right? So he has to move towards its right, correct? So let's try to move towards it, right? So if I say I have to move towards it, right? So my search space will reduce to 5 to 7, correct? So if my search space is 5 to 7, correct? What will be the middle? The middle will be 6. So again, try to find out how many are lesser than 6. So go to the first row. There are 3 numbers that are lesser than equal to 6. There are a couple of numbers that are lesser than equal to 6. There are a couple of numbers that are lesser than equal to 6. So in total of, there are 7 numbers that are lesser than equal to 6. So can I again say my person is standing somewhere where he has 7 numbers including himself that are lesser than equal to. Okay, so do you observe a pattern? Previously, whenever mid was around 8, it was also having 7. So you're moving left, So currently a person is standing and it's saying that I have 7 numbers. So I'll be like, okay, why don't I try to move it to something left? Probably I might get an answer. So I'll be like, okay, let's try to go on the left and try to find an answer. So mid is 6. If I try to go on the left, this 7 will go to mid minus 1, which is 5. So my range will be 5 to 5. So the range is 5 to 5. The middle will definitely be 5. Now let's again figure out how many are lesser than equal to 5. So again go to the first row and you see that there are a couple of elements. Go to the next row, you see that there is 1 element. Go to the next row and you see that there is again 1 element. So in total, there are 4 elements. Yes, in total, there are 4 elements that are lesser than equal to 5. So can I again say the person is standing somewhere where, including him, very important, including him, there are 4 numbers only which are lesser than equal to him, which is 5. So can this guy be the median? I'll be like, no, this guy can definitely not be my median, because in order to be median, I know one thing. If the person is standing here and there are 4 numbers on the left, so including him, it should be greater than 4. It definitely should be greater than 4. Because if he's the guy and he knows there are definitely 4 elements on the left, so including him, there might be a couple of instances, like there was 3, 6. So including him, there definitely has to be more than 4 elements, right? That's why this lesser than equal to is so important. So what I'll say is, okay, this is not possible. So this person will try to go on the left, on the right rather. So when it tries to go on the right, the low will go to mid plus 1 and it becomes 6. So what I can say is, I have shrinked my search space in such a way that I am currently having 6 and 5. Now let's understand the meaning of this. Now, what were we trying to compare? We were trying to compare if we are having something greater than 4 or not, correct? So we figured out, if we took 5, including 5, we had 4 elements. But the moment we switched to something like 6, we started having around 7 and probably more than that. But this was what we observed, and this is the break point. So if you try to write this, you'll actually understand this. 1, 2, 3, 3, and then we had 3, 6, and then a 9, 9. That's actually true, because till 5, we actually had 4 numbers. And right beyond that, because this is the median, right beyond that, we got our answer, because we know if 6 is the median, the number of numbers lesser than 6, because these 4 will be there. but the number of appearances of 6 will be counted. That's 3. That's why you got 7 numbers lesser than equal to 6. So this is the break point. Yes, 6 is the break point. Hence you can say wherever low ends, that's going to be your answer. Yes, this is how you're going to solve this using binary search. Now, a very key point. Now, you're trying to figure out how many elements are actually smaller than equal to mid. That is what you're trying to figure out, right? How many numbers are smaller than equal to mid in the given matrix. So let's now find out the binary search method of doing that. Now, during the binary search, what we were doing is we were figuring out how many number of elements were lesser than equal to mid in the matrix. And in order to do that, we were actually traversing through every row, right? The brute was to just run a for loop and compare. But obviously, that's going to take a lot of time. So what I do is I'll try to implement a binary search on every row. Why? Because the row is sorted in nature. So imagine this is among one of the rows, right? And I'm looking to figure out how many elements are actually lesser than equal to 5. Okay, I'm trying to figure out how many elements are lesser than equal to 5. Again, we're going to implement a similar binary search. So can I say if I can actually point to the index, I repeat, can I say if I can actually point to the index which is exactly greater than this 5, then these guys will be the number of elements that are lesser than equal to 5, because you're pointing to the index that is exactly greater than 6. Now this is done by something as upper bound in C++. Like, I have a video on this. If you want to use an STL function, you can, but in an interview you can definitely not. You have to tell him the binary search approach. So the binary search will be trying to point to this index, right? To this index, so that all the elements to the left of it is actually lesser than equal to 5. So let's try to do this using binary search. So the question boils down to finding the index where a of index is actually greater than 5. So let's start the binary search. So initially the search space is from 0 to 6, because that is the entire array. So just take the middle. So the middle will be 0 plus 6 by 2. That is the third index. So you just go and point to the third index. So your middle is pointing to the third index. Now you're actually looking to figure out which is the first index where it is greater than 5. So what is the value at this third index? It's 5. But what are you looking for? You're looking for someone greater than 5, correct? So obviously, if this guy, I repeat, if this guy is 5 and you're looking for someone greater than 5, you're very much sure that since the array is sorted onto the left and on the current element, you're never going to get your answer. Onto the left and on the current element, you're never going to get your answer. So my search space will now boil down to only this much, correct? So my low is going to point over here as of now. So once my low has pointed over here, you have to find out the middle again. So if you figure out the middle, you will get the middle as 4 plus 6 by 2 and you'll get it as 5. So the middle now points over here. Now what is the value over here? You see that the value is 6, correct? The value is 6. Now you're looking for someone greater than 5. So you can say that your answer might lie over here, because this is the first element, 6, and that's greater than 5. So you're going to find the immediate index where a of index is greater than 5. So I know something. Either this 6 is my answer, I repeat, either this 6 is my answer, or someone to the left, because you're wanting to find the immediate index which is greater than 5. So I can assume that this 6 might be the answer, but I wanna trim the search space. So let's trim the search space too, because let's assume the 6 can be the answer. So what I'll say is I'll just cut off the search space. And I'll move this high to mid -1. So high will be pointing over here as of now. Okay, so high points over here. So my search space as of now is only this 5. And obviously if I try to figure out the middle will as of now be 4. Okay. Now what is the guy? The guy over here is at 5 and you're looking to find someone greater than 5. You're looking to find someone greater than 5. So what you will do is, this is 5. So this cannot be your answer, or anything to the left cannot be your answer. So you will take your search space low and you'll say, go to the right and find it. So whenever you go to the right, it goes to here, that is over here. So I can say the low crossed high. And if the low crosses high, that means I stop. So where is the low? The low is currently at this fifth index, right? Which means beyond this, all the numbers are greater than 5. And before this, all the numbers are smaller than equal to 5. So can I say low is the starting index? Yes, low is the immediate index where a of index is actually greater than 5. Hence, you actually got your index. And if you got your index, can you answer how many numbers are smaller than equal to 5? Since it is zero based indexing, I can say wherever the index points, so that will be your answer. 5 is the number of numbers lesser than equal to 5. And if you count 1, 2, 3, 4, 5, there is exactly 5 numbers. Guys, remember, whenever you're implementing binary search, it's very important to shrink the search space so that you can at the end get a breakpoint and you can say that this is my first guy which satisfies any given condition, and this is my last guy which doesn't satisfies the given condition, and then you can easily figure out whatever you are required to find. So always try to minimize the shrink space, correct? So this is how you can definitely find the index where a of index is greater than 5, and apparently you can definitely find how many numbers are lesser than equal to 5. So this can definitely be done for every row. So I hope you have understood both the binary searches, correct? Now how will you implement this? It's a very simple task. Now you know the initial search space was from 1 to 10 to the power 9. So why don't you initially have a binary search? So probably you will have a binary search, correct? Inside that binary search, whenever you compute the middle, you just required to figure out how many are lesser than middle, correct? That is what you did. How many are lesser than middle? And if that number, for an example, assume how many are lesser than middle was something lesser than equal to your, for example, 4 was our example, which is n into m by 2. If it was something lesser, you needed to move right, correct? So you will move right. And if it is greater, your person will try to move. Like for an example, there are 7 numbers including your person. The person moves left. So whenever it moves left, it means high minus 1. This is the simple way. And how do you find lesser than equal to middle? Just use a binary search to find the index where a of index is greater than mid. That's it. Couple of binary searches. So this will be your flow of your code. Now let's check out the code. So guys, let's check out the C++ code. I won't be discussing the Java code because both of them are identical. Yes, the only difference is in C++ we use a vector. In Java we use array list. Apart from that, you can just see that everything is for loop and while loop. So in Java also it's similar. So if you understand this, you can definitely code in Java. I'll be leaving the Java code link in the description below. So it has been given a 2D vector, right? A. And what you do is you initially assign the search space. So the search space is from 1 to 10 to the power 9. So I've assigned it. And you compute the number of rows and number of columns in this fashion. Once you have done that, let's implicate binary search. Binary search was very simple. You took low lesser than high, right? That's binary search. And you did mid equal to low plus high by 2, correct? You did mid equal to low plus high by 2. Now, you needed to count the number of numbers which were actually lesser than equal to mid, right? So why don't I write a function which does that? Okay, let's discuss the function afterwards. So I've written a function which counts me the number of numbers smaller than equal to mid. Now this function can be renamed to equal to. Okay, if you have any issues with the function name, you can definitely rename it equal to mid, correct? So this is going to go on every row. Every row will be passed on to this function, and you ask this function to give you how many are lesser than equal to mid. So you count all these, And if that count is lesser, then your guy has to move right, correct? Has to move right. So you move it. Or if this is not, let's try moving left and try to figure out if I can get a smaller answer. Simple. Now this is a simple binary search. You just need to now understand how do you write this binary search. Let's check it out. So again, a simple array or a vector or array list, whatever is given to you, and this is the middle. You need to figure out the immediate index, which is actually greater than middle. So as usual, the search space is L equal to 0 and the size, that's the last index. And what I do is I simply write the binary search condition, which is L lesser than equal to high. And I write int middle equal to, I just get the middle by low plus high by 2. And now I check if this guy is lesser than equal to middle. Well, in the left you can never get the answer, correct? If this is the case, because I'm looking for the value which is greater than middle. I'm looking for that. So if this is the case, my L has to move right. My L has to move right. Or if this is not the case, my high has to move left, because I'm trying to find a breakpoint. I'm trying to find a breakpoint. So I'm going to string the search space. And once I've stringed the search space, I think you did observe that low was your answer. So just return low because that is the index. An index is equivalent to the number of numbers lesser than equal to mid. So this is how this function will help you to find the number of numbers lesser than equal to mid. So once you have done this, you can easily figure out the answer as low, because if you remember the first binary search, the answer was low because that was the breakpoint. So you can definitely return it. Now if I talk about the time complexity of the code, let's analyze that. So can I say you are actually implementing a log base 2, something like 2 to the power 32, because 10 to the power 9 is around 2 to the power 32, like that's the highest integer that you can have. There's a log base 2 to the power 32 binary search that you're implementing. Inside it, you're running for every row. For every row you're running. And in every row, you're implementing a binary search on its column length. So the length of the column is M. So can I say this is my complexity, because binary search on the outer, and for counting the number of elements, this is what I am using. And if I write this, can I write this as 32 into n into log base 2m? For an example, I'm just assuming that this is 32 bits, like the maximum integer possible is given to you. That's going to be our time complexity for this particular binary search. What about the space complexity? Are we using any external space? I don't think so. We're using any external space. Yeah, we are just using, we're making sure we're passing it. We're passing this array of I, but again, that can be easily done by avoiding this pass. You can easily do it over here, just so that you understand the code. That is why I've modularized it, but you actually do not need to take an extra array. So I can say the space complexity is big O of 1, because you're not taking any extra space complexity. That's what the time complexity and the space complexity will be for this solution. So guys, I hope you have understood the entire binary search. Just in case you did, please make sure you like this video if you have watched till now. And if you're new to our channel, do not forget to subscribe it. With this, I'll be wrapping up this video. Let's meet in the next video where I'll be solving one more binary search problem.
Whenever your heart is broken